Look, we all know that shapefiles are, well, but let's take a look inside and see what is actually in here and how spatial file types have changed over time to adapt to changes in technology by looking at 3 different file types from 3 different eras. And then we'll take a look at what all of this has to do with this road in Arizona. So let's start at the beginning and understand why the shapefile was actually innovative for its time. And to do so, we need some Legos. Now we have to remember that the shapefile came out in the early 1990s, and around this time, there was much less computing power than we have today. The previous geospatial file formats for vector data were much more limited and highly specific. Take, for example, the Tiger, or the topologically integrated geographic and encoding referencing data from the US Census Bureau. This file format was specific only to the US Census Bureau, and other agencies around the globe had their own versions of vector data formats at this time. Now, I just want to repeat that each specific government agency had its own file format and file type for geospatial data, and these had very limited compatibility between the different agencies. Then ESRI came along and introduced the shapefile to have a compatible file format that was non-topological and that also supported the quick rendering of spatial data. Rendering data was probably the largest challenge at the time, and the shapefile addressed these needs in a very specific way. And when the shapefile was introduced in ArcView, it gained adoption very quickly because of its cross-compatibility and efficient file structure. Now look, I know you're going to say having multiple different file types in a zip file is not an efficient file structure, but bear with me for one moment. Let's remember again that this period, computers had far less computing resources than they do today. Now, if we take a look at the individual components of a shapefile, you can see that each component plays a very specific role. What allowed computer programs to do this was reference just the pieces it needed to run the specific operation that it needed to perform. Back to the Legos, let's take a look here. So imagine that each Lego here represents one part of the shapefile. The SHP file stored the geometric shape. The SHX stored the spatial index, and the DBF stored the associated tabular data. Then, of course, the PRJ holds the projection data. So when you wanted to render data on the map, the computer only needs to look at the SH file. When it needs to reproject, it can look at the PRJ file, and taking a look at one small part, or Lego block as it were, is really efficient solution given the lack of resources at this time. Now, of course, one of the downsides of this is if you're missing one of these pieces, this entire thing won't work. You need to make sure that all the pieces of the file are there together and correctly zipped up for anyone to make use of them. Just like a Lego set contains instructions, pieces, and a box to keep it all in, the shapefile provided a format that worked great for many years. But things changed when we entered the internet age, which is when we got GeoJSON. Let's jump in our time machines and jump ahead to the early 2000s. Web 2.0 is emerging, which means websites could now be responsive and load new information without having to completely reload the web page. And JSON, or JavaScript Object Notation, was the data format that made all of this possible. JSON is a lightweight data interchange format that quickly gained popularity due to its ease of use, particularly in web applications where it was used to exchange data between the server and the client or your browser. GeoJSON, which was first introduced in 2007, did 3 things. First, it was simple, one single file that is easy to read and write for both humans and machines. GeoJSON is also really flexible. It can represent a variety of geometric shapes and properties that made it versatile enough to handle diverse geodata needs. And most importantly of all, it's friendly to the web. The format's foundation in JSON made it a natural fit for web applications, allowing geographic data to be easily integrated with JavaScript and other web technologies. It's much like the standardization of global shipping containers. I bet you thought that's what I was going to talk about next, didn't you? Look, before the 1950s, global shipping was a slow and inefficient process. Goods were packed in a variety of sizes of crates and barrels and bags, each with different sizes and shapes that made it hard to pack and unload the boats, not to mention each port it went to had its own system for doing that. So in 1956, an American trucking entrepreneur named Malcolm McLean introduced the standardized shipping container. These were uniform in size, allowing them to be easily stacked and loaded and unloaded across different modes of transportations, ships, trains, and trucks, and it became the universal standard for transporting goods to this day. This innovation revolutionized global trade by drastically reducing shipping costs and times, and it became the universal standard for transporting goods to this day. And again, for a time it was good. Web maps were easy to create, and you could share this data in an easy file format across the internet. But once again, things change, and this time in the mid to late 2010s, it was the rise of big data systems. This time, the needs changed from rendering and reading data over the web to efficient processing and analytics-based systems, and this called for a new file format to be created, Parquet. And all of that brings us here to Interstate 19 in Arizona. This is the only US interstate to make use of metric measurements on road signs, and it does so for a specific reason. This road is an extremely important route that connects Nogales, Mexico to Tucson, Arizona, with over $25 billion of trade passing through the Nogales port of entry, including much of the produce that's consumed included the US in the winter months. So it makes sense that this stretch of road still uses metric, and it provides an interoperable measurement format between the two countries or two different systems to understand and use the road, much like the reasons metric was designed to standardize measurements over 200 years ago. And Parquet solved these similar cross-compatibility problems for big data systems. These new systems included things like Apache Hadoop, Apache Spark, and proprietary data warehouses that store data in columns rather than rows to ensure that the data was highly compressed and to make analytical operations efficient. Now in 2019, discussions started to take place on how the specification could be applied to geospatial data, and then development really accelerated around 2021. And all the way to today, GeoParquet adoption has skyrocketed for these three reasons. The first is that the columnar storage format offers significant advantages in terms of compression, data retrieval, and performance, aka these are very small and very efficient files. It also seamlessly integrates into the modern data processing systems like Apache, Sedona and Whereabouts, DuckDB, and other commercial data warehouses like BigQuery, Snowflake, Databricks, and Redshift. And finally, GeoParquet is easy to use. It's a single file that contains and stores all the data you need and the metadata you need, and it's super small. You can pack a lot of data into it, and it is really, really fast to read and perform analysis on. Each time we developed a new file format, it adapted to the changing needs of the landscape. While some file types might not be suitable for more modern needs, I think it's important not to forget why we have them in the first place. But all of this brings me to my last point, which I didn't mention. If you are interested in scalable spatial analytics, using large amounts of data, especially using GeoParquet, then you need to check out this video where we'll discuss the strange concept known as a data lake. So if you're ready, let's jump on in.